When direction came from Yukon College administration about offering a pass option, I was surprised that Yukon College, now Yukon University, I guess I should make the change, that Yukon University defined a passing grade to be a 50%. At the institutions that I went at, a passing grade was a 70%. So that got me thinking about why that would be and kind of what the practical implications from an instructor standpoint having a passing grade of 50% is. I know we have at least one education specialist in the class who has to suffer through all of the criminology and environmental studies kinds of questions. So this one's for you, and for the rest of us, this also serves as an example and an application of using the binomial distribution. We haven't had too many of those. So the specific question that I want to look at is whether or not a 50% passing grade is whether or not it is an effective cutoff. And the way I'm going to look at that initially is comparing or utilizing a hypothetical, so I pretend 20 question true-false exam. So here I have the number of possible right answers. You could get no right answers, one right answer, down all the way to 20 right answers. And for this case, I want to consider a student who literally knows nothing about whatever the material is. So they're taking the test, doesn't know anything, and so they will have to guess on every single question. Now, for this first iteration, this first example, our test is 20 true-false questions. So there's a probability of getting a right answer for any of the questions, which is 1 out of 2. So there are 2 possible options. They will guess one of them. So there is, unsurprisingly, a 50% chance of getting the right answer purely by guessing. And that is the case for each of the 20 questions. I then want to ask, since we're talking about comparing the final student grade to a 50% pass-fail threshold, I want to know, well, given this 50% chance, what is the expected exam score for a student that didn't know anything, that is having to guess on every single question? What grade are they most likely to get in my 20-question true-false exam? So I already gave away the answer on how we're going to do this. It's a binomial question. Hopefully you could look at the setup and figure that out for yourself, knowing that we're going to look for a certain number of correct answers, or a certain number of events happening, given a certain number of opportunities, certain number of questions in this case, and given a certain probability of an event happening for every opportunity. So probability of getting a right answer in this case. So those 3 components lead us to using the binomial distribution, and that is what we're going to do here. We're going to calculate the probability of getting this number of right answers, and then find out what the most likely number of right answers is for the student to get, and use that to calculate their expected exam score. So in Excel, we're going to use the binomial distribution. Start typing binom, see what comes up. We want the binom.dist for distribution. Number underscore s, that is Excel asking for the number of successes or the number of events. For us, events is right answers, that's what we care about. Trials is the number of opportunities, that is for us the 20 questions they're going to be guessing on. The probability of a success, the probability of an event happening, of getting a correct answer, is this number over here. So it's a 50% chance of getting an answer correct just by guessing. And for the binomial distribution, at least the way we're using it, we want false. We want the exact probability of 0. We do not want a cumulative probability. So when we get to 10 right answers, for instance, we want the probability of exactly 10 right answers and not the probability of 0, 1, 2, up to 10 right answers. So false for us. We can see, given a 50% chance of guessing a right answer on any particular question, there is a very, very small chance of getting no answers right out of the 20 questions. So let's expand that and calculate the probability for all of these variations of right answers. We want the highest one. If we just scan across the numbers, we see it is 10. So this is our student is most likely totally guessing by, or putting in random guesses. Our student is most likely to get 10 right answers. We can also highlight all of these, and we just quickly look at the sum. We can see that the student has more than a 50% chance, so almost a 60% chance of getting 10 or more right answers purely by chance. That's slightly more than getting less than 10, which is 40%. So perhaps worth noting. So our most likely number of answers is 10. So the expected exam score is the most likely number of questions to get right, 10, divided by the total number of questions that there were. So if the student was totally guessing, knew nothing, and had to take the exam kind of blind and randomly give an answer for each question, they're most likely to get a 50%. And as we saw, the total probability is about 60%. So they are more likely to pass than to not pass, assuming they know nothing. So if you totally guess, chances are best that they will pass. And so it seems kind of weird to me that if a 50% of a passing grade implies, I'll put this in quotes, implies mastery of the material, if a passing grade means, yeah, you know your stuff, then it seems weird to me that you can get a passing grade going in and completely guessing. So literally not knowing anything and making a totally random guess. So to me, that implies 50% is not a good threshold, at least not for a true-false kind of exam. So there are two ways that immediately come to mind that we could fix this and perhaps do better than a 50% cutoff on a true-false test. The first would be to increase this. So let's make it harder to get a certain number of right answers completely by chance. In the same way that we have a hypothesis test. And in fact, let's go draw this out so we can see what we're talking about. So I'm going to draw it the same way that we normally do. Note that this is the binomial distribution. So what's really happening is we have these fixed probabilities. So 0 right answer is 1 right answer. So there's the 0 right answer. We'd have a bar here that's 1 right answer and a bar here that's 2 right answers. So in reality, this is a discrete distribution. So we would have bars and not a curve. But curves are a lot easier to draw, even for me who draws very bad curves. So we're going to go with that anyway. We have our probability distribution, and here we have our 50% mark. We were saying that is our threshold. And it really does go in the middle. That is the most likely value for us to get. So instead of 50%, perhaps it would be better to have a different threshold out here, such that we had a fixed and a small probability of getting something this large purely by chance. So if a student is totally guessing, if they have a 50% chance of getting a question right, then what is this cutoff such that they have a much smaller probability of getting it purely by chance? And just for grins, let's say this is 10%. So we don't want a student to have any more than a 10% chance of getting an exam score this high purely by chance. So if this looks kind of familiar, it should. This is the same setup that we have for hypothesis tests. And this line here we've been calling a critical value. So it is a distance from our mean that leaves a certain probability. For us, this is exactly what we want. We don't really want a critical value, but we want this kind of thing. We want a threshold, a grade that is a certain distance away from that 50%, where there's only a 10% chance of getting higher than that purely by chance. And they say we don't want a critical value because this critical value would still be in kind of standard deviation or standard error units, and we wanted in original grade units. So instead of a 50%, we want to know, should this cutoff be a 60%, a 65, a 70%, or something kind of like that. So that's what we're looking for. In a hypothesis test, the way we've been doing it, we've used an Excel function to calculate this probability exactly, especially since that's a continuous distribution, like a normal distribution or a t-distribution. We've needed an Excel function to do that. There does exist that function in Excel, .inv function, but we haven't used it in the class, so I'm not going to use it here either. Instead, we have the probabilities, so we're just going to sum it up manually. So we want that upper 10%. So we're going to start at the top and just start adding values until we get up to about 10%. We may not hit it exactly because this is a discrete distribution. So we'll see how far or how close we can get to 10%. So this first value is just going to be that one. And the second value is going to be the value we had plus the next one. And we're looking for this total to equal 10%. So we can see I didn't have to go that high. There's 6%, there's 13%. So let's get rid of those because I don't need them. So it's kind of somewhere in this range. 5% was a bit too low for this example. We wanted at least 10%. So we're probably going to say it's 13. So let us highlight that in a different color, red for instance. So that was our 50% cutoff. So instead of 10 right answers, we're going to say a student has demonstrated mastery. We have demonstrated that they know more than random chance would let them prove if they get at least 13 questions right. So this is equal to 13 questions, right, over 20 possible questions. So from this, we're saying that our threshold, our pass-fail threshold, shouldn't be 50%. That's too low. It's too easy to get that by chance. But rather, for 10%, a pass-fail cutoff of 65% is more reasonable. It is too difficult for a student to get a 65% or better purely by chance. They actually do have to know something. So that's one way of doing this. We could adjust our threshold, our pass-fail threshold. The other way of doing it is make it more difficult to guess the correct answer. So here, initially, it is just as easy to guess a correct answer, 50%. You just have to get more correct answers. Another way to do it, again, would be to, well, let's just make it harder. So instead of a true-false test, for instance, let's go make this a multiple choice test. So perhaps there's an A, B, C, and D option, so 4 possible options instead. So instead of a 50% chance of getting a right answer, totally by guessing, it is now 1 divided by 4, A, B, C, D, so 4 possible answers, only one of them is right, so 25% chance. The way we're going to evaluate this is all the same. We just have a new probability of success, a new probability of our event happening. So we're still going to use the binom.dist function. The number of successes is still the same. We can still get 0 to 20 right answers. The number of trials is still our 20 questions. The probability of success is now 25%. It's more difficult to get a right answer by guessing. And cumulative is still false. We want an exact probability. So now this is still a small number, but compared to the original, we can see it is now much more likely to get no right answers because there's only a 1 out of 4 chance of doing so, purely by chance. So we again look for the highest probability, and we can see it's here this time. I'll put that in orange to match our previous one. So now a student totally guessing on our 20 question, but 4 option multiple choice exam, the student is most likely to get 5 correct answers purely by chance. I put this in the wrong place. That should be equal to 13 over 20, 65%. So our expected exam score for our multiple choice exam is 5 correct answers out of 20. So our student would only be expected to earn a 25% on the exam. So now, if 50% chance, or sorry, if 50% was our pass-fail cutoff, like it was originally, we can see the probability of getting a 50% or above based on this multiple choice test. There's our 50%, 10 or above. Up to 20, that total probability is 1.3, 1.4%, something like that. So by switching from a true-false test to a multiple choice test, we've gone from having a 60, in fact, let's go look at that. Originally, we go from a almost 60%, so a 59% chance of passing purely by chance. And we've decreased that down to a 1.4% chance. So a huge improvement in correctly assessing whether or not a student knows what they're doing by going from true-false to multiple choice test. That's probably good enough for this example. Hopefully that made sense and was kind of interesting for people. If nothing else, again, a bit of a review on applying the binomial distribution and calculating probabilities of specific number of events and probabilities of a certain number of events or more. So in this case, getting 10 questions right, at least 10 questions, passing, or anything higher, in which case you are still passing, and that sort of thing.